Axial loading of a member, and in that case the area of the member was not a constant and it changed with the length of the member, and we came up with these equations, and we also showed you that the work done by the applied force is p squared L over 2AE if and of course so is the strain energy if the load and the cross-sectional area are constants. This is where we were last time. Is that correct? Okay. Now we'll take a look at bending. What we do in bending. And recall that all of this comes from the strain energy density equation, which for linear elastic behavior is that in normal loading, normal stress that is generated either by axial loads or by bending loads. So for normal stresses, that's what we had. And then we said that U, the total strain energy, is the integral of U dV. Strain energy density, that means strain energy per unit volume, times a differential element of volume, and if you integrate that over the whole body, you'll get the total strain energy. In the case of bending, the stress in the material is not a constant, contrary to the axial load when the cross-sectional area and the load are constant, but varies. And in bending, the stress is equal to, remember the equation? Only if you're looking for the maximum stress. But in general, that's not the equation. It's my over I, right? When y is the distance from the neutral axis to whatever element you are looking at. Remember that if you have a case of bending, this is the stress distribution. Linear elastic behavior. Oh my, put one over here too. This still applies. For any point in the material, strain energy density is still equal to sigma squared over 2E. So for example, for this point, the neutral surface, since there is no stress, there's no strain energy density at that point. As you move away from the neutral surface, the magnitude of sigma increases, and so will the strain energy density. Therefore, we have to integrate this by substituting for sigma this value my over I. And if we do that in the equation that I have on the board, we say the integral of U dV equals, and substitute for this now, get the integral of sigma squared over 2E dV. Now we substitute for sigma. And if we do, this is what we get. It's on the screen here, and of course in your handouts as well. Then we recognize that this dA and x are essentially independent of one another, the differentials. So we can take out y squared dA, and the reason why we have a double integral, of course, is because we have two differentials. The integral of y squared dA, and that should be integrated over the whole area, is defined as the moment of inertia about the neutral axis. This is how we define moment of inertia, the integral of y squared dA. So we substitute moment of inertia about the neutral axis, and notice that this I squared is the same thing squared. So one of the i's cancels out, and you get this last equation, the integral of m squared over 2ei dx. And notice how similar this is to the equation for axial loading, the integral of f squared over 2ae dx. And as we will see, all of these equations for the strain energy are very, very similar to one another, and you can deduce one from the other. Any questions? Okay. The next case. Before I go there, there's a top comment here. The equation that we just talked about, appearing on the bottom of the previous page, was found for a constant bending moment. In other words, we said sigma equals my over I. In fact, this equation is found for a constant bending moment. In general problems, you may or may not have a constant bending moment. Although the equation is derived for a constant bending moment, it gives you good results provided that the beam is long, meaning that the length of the beam is at least 10 times the largest dimension of its cross-sectional area. This is the same thing we talked about when we said we neglect direct shear stresses or transverse shear stresses. If that is not the case, and if the beam is short, then not only do you need to take a look at the strain energy due to bending, but you also need to take a look at strain energy due to transverse shear, the VQ over IT term. And we'll take a look at that briefly at the end. In most of the problems that we will be doing here, unless you're told otherwise, you should assume that the beam is long enough so that you do not need to take into consideration the strain energy due to transverse shear. Torsional loading. If we follow the same procedure that we did for bending, for normal stresses, we follow the same procedure, we find that the strain energy density is defined very similar to that in normal stresses. So if this is the stress strain diagram in shear, the area under the stress strain diagram will give you the strain energy density, U. Only due to shear. In most problems that we do, in fact, in our problems that we do, I think, it is assumed that the material is linearly elastic. In other words, the stress strain diagram is not like that, but it's like this. And therefore, in the equation for the calculation of area under the stress strain diagram, we can substitute for tau G times gamma, G being the modulus of rigidity, also called shear modulus. This is tau equal to G gamma. So once you substitute that into that equation, into that integral, then that integral becomes easy to evaluate. You evaluate that and you get this. tau squared over 2g, very similar to sigma squared over 2e in the case of linear elastic behavior. Then we find the total strain energy. We put that in. Once again, we substitute for tau its value, which ranges from 0 at the center of a circular cross section. By the way, all of this torsional loading is assumed to be applied to members of circular cross section. That's the only thing that you have studied so far. You have not studied torsion of non-circular cross section. So that's the only thing we talk about. So this tau ranges from 0. So this was your sigma in bending. That's tau in torsion, starting from 0 at the center of the shaft, for example, and going out to its maximum value. It is a variable, therefore we put in T rho over J. Rho is the radius to the point of interest where you want to calculate the shear stress. So we substitute that, and once again, the integral of rho squared dA will give you the polar moment of inertia. We substitute J for that, and it cancels out one of these J's, and you get this last integral. So U equals the integral of T squared over 2gj dx. And if T and J, the cross-sectional area, and the torque are constants, then this degenerates down to this equation, T squared L over 2gj, very simply. Okay? Any questions? Direct shear, that is an applied shear stress, like this. This is not the transverse shear yet. This is direct shear. If you have a case like this, we say whatever strain energy is stored in this material must be equal to the work done by that force, F, as we've had it before. If this is the deformed shape of the part, and we can see that the force F has moved a distance delta in its own direction. Therefore, its work is the integral of F d delta, if you will, or F dx from 0 to delta. It is not F times delta. Is everybody okay with that? Does everybody understand that? It is not F times delta. If there is linear elastic behavior, it becomes F delta over 2. And that's what I have here, assuming linear elastic behavior. Delta is equal to this length multiplied by that small angle. This is all for small deformations. That small angle is defined as the shearing strain. Remember, shearing strain definition is the change in an originally 90-degree angle. This angle was 90 degrees before the load was applied. It is now this. The change is gamma. That's the shear strain. And this length, which is equal to delta, is equal to L times gamma. Gamma is tau over g. Again, we're assuming linear elastic behavior. Tau is, however, F over A. The shear stress there on that surface is a constant. It's not a variable anymore. A is the area on which the force F acts. So we substitute that into the equation for the strain energy. With delta equal to L tau over g. By the way, let me show you where that comes from. boy. So delta equals L gamma, gamma equals tau over G. You substitute for gamma, and you get this equation. And you can also substitute for tau if you want it in terms of F. There is substitution for gamma, L tau over G, substitution for tau as F over A, so you get FL over AG. A is the area on which F acts, one more time. Substituting into the equation for the strain energy, this is what we get. And there is no integral in here because the shear stress in this case is a constant. It doesn't change. Not similar to the bending and torsion case. A summary of all of these loadings. As I said before, they're very, very similar, and you can deduce one from the others. This is normal stress, U equals sigma squared over 2E. Shear stress, tau squared over 2G. Torsional shear stress, tau max squared over 4G. I have not proven this. I just wrote that there without any proof. The proof of that is a homework problem that you see at the bottom of this page. It says, show that that's the case. So that's up to you to do that. For shear due to transverse load, this is the VQ over IT term. The equation is very, very similar. For the time being, forget that C. Everything else is exactly the same as the shear stress, that shear energy deformation, energy due to shear deformation that we had. We had F squared over 2AG dx is now V squared over 2AG dx. The only difference is that the shear stress is no longer a constant. The transverse shear stress in beams varies like that. It's maximum at the neutral surface, and it's zero at the outer surfaces. Therefore, we have to use the integral. That's not a constant. This constant C is related to the shape of the cross section. And it's given for some common cross sections in the table below. So those are the values of C that you use for these sections. And this is what I meant when I said it's a homework. So derive the expression for U in the case of torsional shear given above, that equation. You should prove that that is the correct equation for torsional shear stress. Any questions? Okay, now that we are through with the definition of strain energy, here is its application. In ME 219, you learned a few methods for, including this one, by the way, for finding deflections in beams. We will do that here using Castigliano's theorem as well. Not only deflections in beams, but any type of a deformation. Axial deformation, torsional deformation, bending deformation of any sort. So this is one method of finding these deformations. And let's spend a few minutes on making sure that you understand this paragraph thoroughly. All of Castigliano's theorem is in those 4 lines. So it says, when point loads, forces, moments, or torques. By loads, we mean any one of these. It's not just an axial load or even a force. It could be a moment, could be a torque, could be a force. So we call them loads. Any kind of load. The important word here is point. You might want to underline that. When point loads, not distributed loads, point loads, act on a system that undergoes small displacements, linear or angular. In torsion, it would be angular. In bending, it would be at least partially angular. In axial loading, it would be linear. The displacement of any point of the system in the direction of the applied load at that point, I'll draw a little general sketch for you in a few seconds, is equal to the partial derivative of the total strain energy of the system due to all loads, not just that one load, with respect to the load acting at the point. In other words, that. So what do I mean by that? Let's say here's your system. It's under forces, moments, torques, whatever. And there's a force acting here. We'll call that force F. I would like to know that under the action of all of these loads that are on this system, how much does that point move in the direction of that force? So very important. A point load, number one. It could be a torque, it could be a moment. But in this case, it's a force. Point force. And I'm interested in its movement in its own direction. Whether it's in this direction or in the other direction, sense that is, it doesn't matter. It's got to be in the direction of that single force. Is equal to the partial of u due to all loads. Strain energy due to this load, due to that load, due to that moment, due to that force itself as well, included. We find the strain energy, then we take the partial derivative of that with respect to the force that acts at the point of interest. The reason why we say partial derivative and not total derivative is that u, the strain energy, is not just a function of F. It's a function of the other loads applied as well. So we want its partial, however, with respect to F. If you do that, you will have the deflection. Angle of twist would be partial of u with respect to T, a torque, point torque at that point. We'll do some example problems there. Any questions? Okay. Now, in order to find the value of u, you have to include the strain energy due to every single force. A question that comes to mind is this. What if I'm interested in the deflection of that point in that direction? Call it delta 1. Call that point 1. And we do this so this doesn't look like a force. And there is no force at that point, whether in that direction or any other direction for that matter. In a case such as this, what we do is we introduce what is called a fictitious force, one that doesn't really exist, in the direction of interest. Fictitious force in the direction of interest. And we treat it as though it were an applied load, except that its magnitude is not known. So we find strain energy due to all loads, including FF. We take the partial with respect to FF, and once we do that, we set the value of FF equal to 0. That way we'll find the deflection delta 1 in the direction of that force called the fictitious force. Is that clear to everyone? You should have done some of this in 219 at least. Okay? The same thing is true for a moment or for a torque. If there is no load there, you put in a fictitious load there. Insofar as this integral and the partial are concerned, of course we can evaluate all of this in terms of all of the applied loads and then take the partial. Nothing wrong with that, and you will get the correct answer. However, it is also possible to take the partial derivative of u with respect to f before we evaluate the integrals. Take the partial beforehand, and you end up with this. And remember that the partial of, for example, m with respect to m squared with respect to m is equal to 2 times m, the partial of m with respect to f, as an example. Everybody follows that, right? Just rules of differentiation. M is a function of f. Everything else in that equation is not a function of f. So axial load, partial of f with respect to the load. Bending moment, partial of f m with respect to the load. Torsion, this is transverse shear. You need a C here. I think it is in your notes, correct? Yeah. So that is correct. Don't cross it out. What's on the board is not correct. So you need a C there. And that one. The reason why this is better to do is that you won't have to square the moment. Otherwise, you would have to use the previous equation, you would have to use this equation where you can see all of the loads are squared. So you have to do that squaring first, then find u, and then take the partial. This way you eliminate the need for taking that, for squaring the moment or torque or axial load, whatever else it may be. So, once again, in the cases of constant torque or constant force and constant cross sections, we get these values that we've had before. And this is shown in here just as an example, that if you take the partial of u with respect to the force F, this is for axial loading. You get FL over AE, the deflection in axial loading. I think I talked about this last time as well. And if you take the partial of u due to torsion with respect to t, you get TL over GJ, which is the angle of twist. So these simple cases jive with what you already know. Any questions? Okay, let's take a look at some example problems. This is from your handout. And the first one is problem 1017. All of these problems, by the way, are from the Strength of Materials book by Beer and Johnston. An older edition. You may not find these exact problems in the newer editions. So in this problem it says a uniform 3/8 of an inch diameter rod AB of length 9 feet is made of a high strength stainless steel for which sigma y equals 125 ksi and E equals 28 times 10 to the 6 psi. Knowing that a strain energy of 50 foot-pounds must be acquired by the rod as the axial load P is applied, determine the factor of safety for the rod with respect to permanent deformation. It means yielding. So this is the rod. There is the force P. Rod is of length L. Like that. We have, from the strain energy equations, that the strain energy for axial loading is equal to P squared L over 2AE. Notice that in this case, both the force and the cross-sectional area are constant. So U equals P squared L over 2AE. We need, for the strain energy in this whole rod, to be equal to 50 foot-pounds as it's given. So U is 50 foot-pounds multiplied by 12 to get it in inches. P is not known. If it were known, it would be a simple matter of finding the factor of safety. It's not known. So that's our unknown, P squared. The length of the beam is 9 feet. The cross-sectional area, say 3/8 of an inch diameter rod. So pi over 4, 3/8 squared. That's A. And E is given as 28 times 10 to the 6. One equation, one unknown for P, and you solve for P. P comes out to be equal to 5,860 pounds. We would like to find the factor of safety with respect to yielding, so we have to find the load at yield. So the factor of safety is equal to P yield divided by P. And that's equal to 120 KSI times pi over 4 d squared divided by 5,860. And that'll give you 2.35. Any questions? Is everybody clear on what I did? Find the load that gives you that strain energy, compare it with the load that gives you yield. Yes?
Did you get the
120, is it 120 or 125 KSI yield strength? 125, sorry. Thank you. 125. Yield strength of the material. To find P yield, I multiply the yield strength by the cross-sectional area. So this is SY, and that's A. Okay. Any other questions? Next problem, 1042. Do I call them 1042 in yours too? No, I call them problem 2. Okay, problem 2. 1042 in my notes. This is the problem. The reactions, of course, are not given. These are supports. But if you take a look at the beam and the loading, these two are supports. Because of symmetry, these two loads must be equal, and each of them, therefore, must be equal to 2 kips. So the problem says this. Using E equals 29 times 10 to the 6 psi, determine the strain energy due to bending for the beam and loading shown. Ignore the effect of shearing stresses. This is the VQ over IT part that we were talking about. In most cases, as I said, we neglect that. Contrary to the previous problem, the load here, which is the moment, is not a constant. And therefore, we can't use an equation similar to that, like m squared L over 2EI. If you draw the moment diagram for this, what do you find for the moment in the middle? Not quite. The moment in here is not 0. The shear force is. The moment is not 0. The shear force. Shear diagram for this is like this. Right? With this value equal to 2 in kips. The moment diagram looks like this. And its magnitude is equal to the change in the area under the shear diagram. From here to here is 2 times 15. Oh, sorry, inch kips, not inch pound. Inch kips. So it's 30. You do not need to draw shear and moment diagrams for these problems. In fact, because we neglect, in most problems, we neglect the transverse shear contribution to the strain energy, you don't even need a shear diagram. Don't draw a moment diagram either, because unless you find the equation, the moment diagram by itself isn't going to do you any good. Therefore, although I've done this just to show you how this is, but here's what we do. We recognize that the moment in this section and in this middle section are different, as you can see. Variable here, constant here. So we need to divide this into 3 parts. This part, the middle part, and the part on the right-hand side. For each part, we find the strain energy, and then we add them all up. We also recognize that because of symmetry, however much strain energy is stored here, exactly the same amount is stored here. So we'll just find it for 1 and multiply it by 2. So we have to find it for 2 locations. To do that, you need to draw a correct free body diagram, not at any specific point, but at a general point. You're trying to find an equation for the moment in this section. So there is that section. A moment here, a shear force, this distance is not 15 inches, but x. Again, a general moment equation. And once you write your equilibrium equations, you find that m equals minus 2x. All you need to do is take moments about this point. Let's say counterclockwise positive, positive m. This has a moment of 2 times x, also positive. So m plus 2x equals 0, so m equals minus 2x. Everybody okay with this? This is what you should be able to do relatively quickly. Once you find the equation for the moment, take the partial with respect to whatever it is right then and there if you're doing a Castigliano's problem for deflections. In this case, we're just finding u. But if we were, I would take the partial right here. So this is the first part. I'll call it m1. For m2, I'll have this configuration. The distance from here to here now is 15 inches, and that's the value of x. So m2 will be equal to minus 2x plus 2 times x minus 15. Okay? Now, we use our general equation. U equals the integral of m squared dx over t to ei equals the integral. The first moment is valid. We should write that as well. This is valid for x less than or equal to 15 inches greater than 0. This is valid for x less than or equal to 75 inches and greater than 15 inches. If there is anything you don't understand, please let me know, because we need to get this straight from these simple problems so that when you do get to a somewhat more complicated problem, you will be comfortable. The first one, well, let's say I'll put a summation sign in front of this integral. In other words, both for m1 and m2. So the first integral goes from 0 to 15 of m1, that's minus 2x squared dx divided by 2ei. I'm just going to leave that in terms of ei, and then we'll substitute at the end. Plus the integral from 15 to 75. Remember that I'm writing everything in terms of x, and I should integrate this wherever this moment is valid. Negative 2x plus 2 times x minus 15 squared dx divided by 2ei. And notice that this is 30 kipinch, which of course you expect, because the moment there has to be a constant. And as you saw from the moment diagram, has to be equal to 30 kipinch. In this case, minus 30. By the way, note that it really doesn't make any difference whether this is plus or minus. You're squaring the term. Whether you bend this upwards or you bend it downwards, you're storing energy. It's like compressing a spring or extending a spring. Doesn't matter. You're storing energy. So you integrate that, put in the values of x, put in the values of E and I. They give you the cross section. The cross section for this is 1.5 inches by 3 inches. So the cross section looks like this. Calculate I, put in the value of E, and you get U equals 322 inch-pounds. If you continue with this, you're going to get it in kip inches. Actually, it may be actually kip inch rather than, let's see. Yeah, this is inch kips rather than inch pounds. That's the strain energy stored in the beam. Any questions?
It's also from 75 to 90 as well, right?
Ah, yes, thank you. Therefore, put a 2 there. The portion on the left and the portion on the right store the same amount of energy. So 2 times this first integral plus that. Thank you for that. Any questions? Okay. Let's see, what time do we have? Time for a break. Let's take a break. Okay, problem 3. So it says aluminum rod AB, and they give you G and for AB, G equals 26 GPa. For BC, G equals 39 GPa. Bonded to the rod BD rather than BC. I've marked it BC. Well, I might as well do BC. C here, D here, BD. Knowing that portion CD of the brass rod is hollow and has an inner diameter of 40 millimeters, determine the total strain energy of the two rods. So, in this case, you have a torque applied, and you would like to find the strain energy for that. Clearly, we have three sections here, not because the load is changing, but because the cross-sectional area is changing. We can find the strain energy in each one of these three and add them all up. For each piece, the torque is constant, the cross-sectional area is constant. For each piece, the torque is constant, the cross-sectional area is constant. Therefore, we can use this equation. For each piece. Of course, the value of J will have to be found for that particular piece, and so for the value of G. Let's find J. JAB is equal to pi over 2 times r to the fourth. And in this case, r is 18. I have done this, I'll show you something in millimeters in just a minute, but I've done this in meters. So let's put it in meters. This is 164.9 times 10 to the minus 9 meters to the fourth. JBC is equal to pi over 2 times 0.030 to the fourth. And that will be equal to 1.27 times 10 to the minus 6 meters to the fourth. And finally, let me put that up in here, JCD, pi over 2 times 0.030 to the fourth minus 0.02 to the fourth. 1.02 times 10 to the minus 6 meters to the fourth. Even though I have done everything in this problem in meters, you will save yourself a lot of time and sometimes agony if you do not convert everything to meters and talk about kilonewtons and all of that. In the metric system, and for all problems, if you use newtons, millimeters, and MPa, everything will come out correct. You don't have to worry about, do I need to multiply by 10 to the 6 or divide by 10 to the 6 or 1,000 or 0.001, none of that. And it's very simple to recognize this, because if you look at the simple stress equation, from a dimensional point of view, this is newtons, divided by meters squared. That's the way we usually do it. It's called a Pascal. And it's a very small number. By the way, how much is a Newton? Newton is a measure of force, right? So approximately what's your weight in newtons? Nobody asked you that before? It's very simple. If you remember one conversion, which is actually a wrong conversion, but it works, that a kilogram is approximately 2 pounds. That's a wrong conversion because kilogram is a unit of mass, pound is a unit of weight. But what we should say is that the weight of a body whose mass is 1 kilogram is approximately 2 pounds. If you remember that, so here's 1 kilogram, multiply that by 9.81, the acceleration of gravity, call that 10. That's 10 newtons. And that's approximately equal to 2 pounds. That's 1 kilogram, right? It's equal to 2 pounds. So 10 to 2. So if you weigh 150 pounds, multiply that by 5, you get 750 newtons. Sounds big, but that's essentially 150 pounds. All right? So it's good to know. So when you get a number, at least it should make sense, whether it's in the metric system or in the English system. So you won't write stuff that doesn't make sense. Coming back to this, I will write if this is equal to Pascal. But that Newton divided by meter squared times 10 to the 6 is equal to newtons divided by millimeters squared, right? Because each millimeter is 10 to the minus 3 meters. 10 to the minus 3 times 10 to the minus 3, 10 to the minus 6. And goes to the numerator and becomes 10 to the plus 6. And this is called megapascal. So if you use newtons, millimeters, and megapascals, you don't have to worry about conversions. Keep that in the back of your mind. It does come in handy, even though I've done this in meters, though. Okay, going back to the problem, let's calculate the value of u. A simple substitution into the equation. And this is what you get. U is equal to, for the first part, 800 squared times 0.4, that's the length, divided by 2 times 26 times 10 to the 9, the value of g, times 164.9 times 10 to the minus 9. Add to that 800 squared, second part, 800 squared, length is 0.375. G is, is it 2? Yeah, I have the 2 here. 2 times 39 times 10 to the 9 times J. And for that one is 1.27 times 10 to the minus 6. Add to that 800 squared times 0.25 divided by 2 times 39 times 10 to the 9 times 1.02 times 10 to the minus 6. You evaluate all of that, we get 34.3 joules.
If it's hollow, aren't actually subtracting it or no?
I did. I already have done that.
Okay.
Right? I took it into consideration in the value of j. But along the same line, can we do what was just suggested? Don't calculate this like this. First, calculate the strain energy for this whole thing as though the whole were not there. Subtract from it the strain energy due to the whole. Can we do that? Principally, yes. There's nothing wrong with it. All you're doing is adding and subtracting. But in order to do that, you need to use this equation. Agreed? What do you use for the value of t for the whole? I don't know either. If you do that, it is principally correct, but it's much, much more difficult. You have to solve an indeterminate problem first, find out the value of t for the whole, and so not worth it. That's the easiest way. Okay? But there's nothing wrong with the principle. The principle is correct. Any other questions? Okay, problem number 4. In this problem, you're asked to find the reaction at the right support, at the left support, sorry, this reaction. Clearly, this problem is indeterminate. And therefore, you cannot find that reaction using equations of equilibrium. You did this in 219 as well. So what we do is this. And here we're going to do Castiglianos. I'll call this A, B, and C. In almost all of the problems involving Castigliano's theorem, we usually solve the problems symbolically, without numbers generally. And then if you have numbers, you can input them later. So remember what Castigliano says, that the deflection at any point due to a point load, in this case that point load is actually a reaction, due to a point load is equal to the partial derivative of the strain energy due to all loads with respect to that point load. And then we said that if you take that partial before the integration, life becomes much simpler, and therefore we looked at these equations. as you can see, the only thing we're going to consider here is strain energy due to bending and not transverse shear. As I said before, you should neglect that unless specifically told not to. Clearly, the moment in this section and the moment in that section have two different functions. So we need to take two sections, one here, section 1, and another one here, section 2. So, section 1. M1 equals RAX minus W x squared over 2. In reality, what you do is take moments about this point and set it equal to 0. Equilibrium equation. I have skipped, and then you take things to the other side to find the moment. I have skipped the one step in that. But if there's anything you don't understand in what I wrote and why things look the way they do, please tell me now. Is everybody clear on this, especially on this part? That makes sense to everyone? Because this is what you're going to have to be able to do relatively quickly. Okay. If not, I'll write an equilibrium equation. In fact, I may write an equilibrium equation for the next one anyway. The next one, and for M2, section 2. Not worried about the shear force because we're not going to take that into account. And besides, when I do moment equations, I take moments about that point anyway, so the shear force drops out. So summing the moments about this point, moments about section 2, and assuming counterclockwise positive, will give me this. M2 minus RAX plus the moment of the distributed load about this point. That distributed load can be replaced by a point load at its centroid, and therefore the moment of that about this point is WL over 2 times x minus L over 4. Everybody clear on this? Just an equilibrium equation, nothing major. The distance from here to here is x minus half of that. That's L over 2. Half of that is L over 4. Take the partials right here, right after you find the moments. So partial of M1 with respect to RA. Remember what we want to do. We want to find the deflection at this point as though our wave were an actually applied load. And then set that deflection equal to 0, because there can be no deflection at that point. So we're trying to find the deflection in terms of RA, set it equal to 0. This is x. Take partial of M2 with respect to RA. That is also x. So you set this equal to 0, and M2 will be equal to RAX plus WL over 2 times x minus L over 4. Okay. Now we use Castigliano's theorem, which says that delta A, the deflection at point A, is the summation of mi over ei, I, just in case they're different, times the partial of mi with respect to Ra. I say the summation of that integral because I get one part from this free body diagram and I get one part from that free body diagram. Summation of the two. It is strain energy due to all loads on the body. So this will be equal to the integral from 0 to L over 2. First m is this. Rax minus wx squared over 2 times the partial of m1 with respect to Ra, which is x, dx. And I'll put the 1 over ei here in front. Again, if there's anything murky, let me know. Plus the integral from L over 2 to L of m2, 1 over ei, same way, Rax plus WL over 2 times x minus L over 4 times the partial, which is x, dx.
I think it's minus for M2, RAX minus WL over 2.
Yes, thank you. Thank you very much. However, this deflection in the direction of that load, Ra, remember this deflection is in the direction of the load, vertical, cannot exist. It must be 0 because you have a support there. Set that equal to 0, evaluate the integral, put in the limits, one equation, one unknown, that unknown is Ra. You solve for Ra. Ra comes out to be equal to 15 over 64 WL. Now, when doing these problems, yes?
Is it second integral from L over 2 to L or 0 to L?
No. L over 2 to L.
Oh, okay.
Remember how I did this. In the first free body diagram, x starts from here and goes to L over 2. In the second free body diagram, x starts from the same place and goes all the way to L. But we're evaluating the moment in this section. Now your question may be, can I take x from here? The answer is yes. But then you have to find the moment at this point and the shear force at that point and all of that. Yes, you can do that, but that's a lot more work. So the second one is L over 2 to L. One of the ways that you can prevent some of the errors that you may be making in solving these problems, not the plus and minus like the one I just did, but if you, for example, this is WL over 2 times L over 4, so WL squared over 8, right? Maybe you just write WL over 8. Then what's going to happen is at the end you're going to end up with something like this. You're going to end up with Ra equals something times WL plus W. Because you dropped an L someplace, right? this doesn't make sense. Unit-wise, this should be correct. You cannot add WL to W. Apples and oranges. So if this is WL, that should be WL. If this is W, that should be W. This is one way to check. Take a look at your answer and make sure that it dimensionally makes sense. If it does, it doesn't mean it's necessarily correct. It just means it dimensionally makes sense. But if it does not dimensionally make sense, then for sure it's not the right answer. And you should take a look and see where you made the error. Okay? Any questions? Of course, once you find RA, this becomes a simple statics problem you can solve for their other reactions as well. Any questions? I'm going to start a problem which I know I'm not going to be able to finish, but just to start this fifth problem. Any questions on this before I erase? So in this one, you're asked to find the deflection at this point. Considering only bending moment. There will be axial loads here, there will also be shear loads, and there will be bending moment, but we only consider bending moment. All of the moment equations that we have, all of the equations that we have for stresses in bending cases are for straight beams. We did not talk about curved beams. However, if this length, the length of this beam, is large compared to the dimensions of its cross-sectional area, we can find an approximate value for the deflection if we use the equations for a straight beam. Otherwise, we cannot do that. The stress distribution in a curved beam is not linear. It is not like your MC over I equation. It's not like this. It's more like this. That's the stress distribution in curved beams. And on one side, you have a higher stress than the other side. The two stresses on the two sides are not equal. So we will, however, the larger this gets, the more this approximates that. So we assume that that's valid in this case. We have to write a moment equation, so we take a general section again, nothing particular. There is P, and here we will have a bending moment, a shear load, and a normal load. Now, the directions of those, whatever they are, I'm not saying those are the correct directions. Remember, these are unknowns. You take them in this case, in any direction you want, and if you get the negative answer, that means you have to change direction. That's not the right direction. This angle I will assume to be theta. In general, you would have to take into consideration the strain energy due to normal loads, shear loads, and bending moment. But we will only consider bending moment now. So I need to find the value of this bending moment. So I take moments about this point, call it C. Summation of moments about C is equal to, taking counterclockwise as positive, we get a positive bending moment right here, M. Then the moment of this force about this point is clockwise, and therefore negative, equal to P times what? Statics should be like this now. What's the moment arm? Isn't that the moment arm? That's simply equal to r sine theta, isn't it? So minus p r sine theta, and that's equal to 0. That's the moment. We'll continue on this next time. And once you're finished writing, please put away everything so we can have a quiz. Again, remember, no notes. Book is okay. A sheet of equation is also okay.